guys, welcome back to TechDose, and in this video we will look at count number of balanced permutation problem, which is from Leetcode number 3343. This problem will be based on recursion and memoization dynamic programming. So there are a lot of prerequisite for this problem, but I will be explaining the Fermat's little theorem in this problem, as well as the modulo multiplicative inverse and how to find MMI using the Fermat's little theorem. We will also be learning the basics of counting the permutations, but I expect that you will already watch my video on binary exponentiation as well as the 0-1 knapsack dynamic programming. So I assume you know both these topics, and the link for them will be present in the description below, so please go there and watch. So this entire solution is kind of math heavy, so you can say number theory plus dynamic programming. So you can make out that you may not understand in one go, so you may have to watch it multiple times if you are a beginner for dynamic programming. Now let's read the problem statement. In this problem you are given a string num. A string of digits is called balanced if the sum of the digits at even indices is equals to the sum of the digit at odd indices. Return the number of distinct permutations of num that are balanced. Since the answer may be very large, return it modulo 10 to the power 9 plus 7. A permutation is a rearrangement of all the characters of a string. Now, if you look at an example num, then in this case, you have the number as 1, 2, 3. So, you can actually rearrange the digits at any position. So, if you try rearrangements, how many rearrangements can you do? In this case, all the digits are unique. So, you can say n factorial rearrangements will be possible, which is 3 factorial. That means 6 rearrangements, right? So, if you look here, these are the 6 rearrangements which you can have. Now, if you look a rearrangement like 1, 3, 2, then in this case, if you look at the even indices 0 and 2 and add the digit, the sum value at the even indices is 3. Now, if you look at the odd index, there is only one odd index, which is 1. So, the sum of the digits at odd indices is equals to 3. So, since the sum of the digits, all the digits at even indices equals sum of all the digits at odd indices, therefore, this permutation here is a balanced permutation. So, this will be contributing plus 1 to the count. Okay. So, you have to find such contributions, right? So, 132 is one such number, 231 is also a number because the digits at even position 0 and 2 have 2 and 1 value. So, if you add it is 3, the digit at odd position is 3 as well. So, they both are equal. Therefore, 231 is also balanced permutation. Rest any permutation is invalid. If you look at 321, then 3 plus 1 is 4 and the odd digit number 2 is only 2, right? So, you are not finding them to be equal. So, this is invalid. So, you have to count such permutations, and that is how you get answer as 2. So, I hope we are clear with this. Now, if you follow the simple approach, then you may have to generate all the permutations of this number, and generating all the permutations can be considered minimum n factorial, right? And then only you can parse and get the sum of the odd digit position and the even digit position. Now, if you look at the constraint 80, definitely this is a very high constraint as compared to factorial. So 80 factorial is a very large number, right? Even 20 factorial will not fit in your integer range. So definitely we cannot solve it by n factorial. Whatever we solve it with should be having computations less than 10 to the power of 8. Otherwise it is not going to run within 1 second. So the num's length in this case, the number which is given is minimum 2 length and maximum 80 length, which is a very huge number, right? If the num's length is let's say 9, then it will be hitting the limit for 32-bit integer. If it is 18, then you can assume it will hit the limit of 64-bit integer, right? But 80 is a very high number, as you can compare, right? Now, num only consists of all the digits from 0 to 9, since it is a base 10 number system, base 10, right? So, you have all the digits from 0 to 9. I hope the problem statement is clear. Now, let's understand something about modular arithmetic and then the Fermat's little theorem. So, according to modular arithmetic, you can write a plus b mod of m equals a mod of m plus b mod of m whole mod of m. Same goes for subtraction and same goes for multiplication. But for division, this is not applicable. If you write a by b mod of m, then this is not equals to a mod of m divided by b mod of m whole mod of m. Okay, so these two LHS RHS are not equal. In case of division, you have to convert it to the format of multiplication so that you can make the multiplier, you can actually push the mod inside. So there is a proof for it, but this is out of the scope of this particular problem. Okay, you can easily read the proof of all these things. Now a by b mod of m will be considered as a times x mod of m, where x is equals to 1 by b. X is equals to 1 by b. So if you write it in a multiplication format, then you can easily push this mod to both a and x. A mod of m multiplied by x mod of m whole mod of m. Okay. So in this case, since x is equals to 1 by b, I will be calling x is equals to inverse of b. Okay, inverse of b. Fine. Now I hope you have understood that. So let's now understand how to find the modulo multiplicative inverse, because whatever we saw previously, x is the modulo multiplicative inverse of b. You can say mmi of b is equals to x in this particular scenario. So that is what we will learn now. Let's say that the actual number is n, and if I assume n times x is congruent to 1 mod of p, this is not an equality symbol, it is a congruent symbol. Okay, n times x is congruent to 1 mod of p, then in such case I can say that x will be a modulo multiplicative inverse of the actual number n. If you take an example, let's assume the actual number is 5, and if you take 5 times 3 mod of 7, what is 5 times of 3? 15 mod of 7 is equals to 1, remainder is 1. So if 5 times 3 mod of 7 is congruent to 1, that means equals to 1, then you can say that 3 is the MMI of 5. Okay, I think it is clear. So if you want to find MMI of 5 under modulo 7, then the answer is 3 in this case. But can we have only one modulo multiplicative inverse or multiple of them? If you take another example, 6 by 2 mod of 5, then let's say we need to calculate the MMI of 2 so that I can remove this division operator and convert it to multiplication. So what should I multiply with 2 in such a way that under mod of 5 the value comes out to be equals to 1? Well, if you try, then you will see 3 is one option, where if you multiply 3 with 2 it will be 6, and 6 mod of 5 is 1. So 3 can be called as a modulo multiplicative inverse of 2. Okay, and so this will be true, but is there only one number called 3? No, you can also try with 8, where you can say that 8 times 2, which will be 16 mod of 5, will also be 1. So 8 is also MMI of 2. Also you can say 13, where 13 times 2 is 26, mod of 5 is also 1. So 13 is also an MMI of 2, right? So for any given number, if you have one modulo multiplicative inverse, then you will have infinitely many modulo multiplicative inverses. Okay, and those all will be true, because we are not giving equality, we are giving congruence operator. Now the MMI is not possible for all the numbers, that you should remember. If you see this, 12 has no MMI under modulo 6, because if you multiply 12 with one number, like whatever number you can choose, under modulo 6, how will you get 1? Because 6 can divide this 12. Okay, so whatever you take here, it does not matter whether you take a prime number or a non-prime number, it does not matter. But if 6 can divide this 12, then the modulo will never be 1. It will be 0, right? It will always be 0. So the MMI concept is only possible if this number n and this p are actually co-prime numbers. That means the GCD n comma p should always be 1. If it is not 1, if they are not co-prime, then you can never find the modulo multiplicative inverse of n under modulo p. So how to make sure that MMI of a number is always possible? Whatever number you choose as n, I want to make sure that MMI can always be calculated. In such cases, I will take p to be a prime number, because if you take p to be a prime number, I don't care what is the value of n, it will always be co-prime. Unless n becomes equals to p itself, it will always be co-prime, right? So I will take p as the prime number. So in the problem statement, you will see that if you move up, it was mentioning that the answer is very large, so you need to take modulo 10 to the power 9 plus 7. This is a prime number. Okay, this is a prime number. So if you assume it to be the value m by which you take the mod, then you can always assume that whatever number n you take, n comma m, the GCD of it will always be equals to 1, right? So I hope you have understood this, the modulo multiplicative inverse. Now how to find modulo multiplicative inverse? Well, there are two popular techniques. One is the extended Euclidean algorithm and another one is the Fermat's Little theorem. We will be going with the Fermat's Little theorem. If you know extended Euclidean, you can also go with that. Now according to Fermat's Little theorem, a to the power of m minus 1 is congruent to 1 mod of m. Okay, now if you want to look at the derivation, this is out of the scope of this video, but you can always look at CP algorithms or any math block to actually get the entire derivation of this, right? So according to Fermat's Little theorem, a to the power m minus 1 is congruent to 1 mod of m. Okay, now here the GCD of a comma m, GCD of a comma m must always be 1. Only under this condition this formulation is valid. Now if I multiply a inverse, that means a to the power minus 1 on both the side, then a to the power m minus 1 becomes a to the power m minus 2, and this 1 becomes a to the power minus 1. Now since this relation is symmetric, okay, this entire relation, congruence relation, is symmetric, so you can move this on the left and you can move this on the right, and you can write a to the power minus 1, that means a inverse is equals to a to the power of m minus 2 mod of m. Okay, so using this formulation you can actually calculate a inverse. Okay, you can calculate a inverse all the time. And how do you calculate that? Well, calculating a to the power m minus 1 in the fastest way possible would be by using modulo binary exponentiation. In my previous video I have already explained you binary exponentiation. In case of modulo binary exponentiation, you just have to take a mod function. The entire code of binary exponentiation is same if you look here. Okay, if you look on the right hand side, if I want to find a to the power m minus 2 mod of m, then I will be passing a here, the m minus 2 will be passed as n, and this m is m here. Okay, now what do you follow? If there is a odd power, then we will save it into the result as I have explained already, and we will be squaring the base and halving the exponent, and we will keep going one step after another. If you follow this step, then the time complexity is going to be order of log m and exactly log m minus 1 base 2 steps. Okay, so if you want to calculate inverse of a, then you need to calculate a to the power of m minus 2 mod of m. So I hope this is also clear about how to find the modulo multiplicative inverse of any number using the Fermat's Little theorem, right? Now once that is clear, let's jump on to the permutations. So in this case, if I assume a 6-digit number, then you can find the number of unique arrangements by taking n factorial, where n is the length of this entire number, that is 6 here. A factorial, that means the repetition of 2, that is 2 is repeating 3 times, so a factorial will be 3 factorial. B, which is repetition of 5, 5 is repeating 2 times, so 2 factorial. C, repetition of the third number, that means the third digit, which is 3, it is repeating only 1 time, so 1 factorial. So in the denominator you need to take the factorials of the groups. Okay, like each of the unique digit, how many times they are repeating, you have to divide with that, right? I hope you already know this. So what we need to calculate is n factorial by a factorial, where a is the repetitions, and in this particular problem the a and n are less than equals to 80. So if you remember the constraints, if you look here, this num's length is less than equals to 80, right? So 80 factorial is a very large number. Okay, it cannot be contained in a 64-bit integer, or it cannot be contained in integer even. So that is why the problem had already mentioned that we have to take mod of m so that we don't overflow. Now if you want to calculate mod of m in such a way that I give you a calculation for 80 factorial by 40 factorial, we know that we cannot directly, push this mod to both of them. Like 80 factorial mod m by 40 factorial mod of m whole mod of m, this is not true. This is not true, okay? So in such cases, we need to use the inverse. That means 80 factorial multiplied by inverse of 40 factorial mod of m will be equals to, now you can push mod of m inside, and you can write 80 factorial mod of m so that you avoid overflow for each of these unique items as well. Inverse of 40 factorial mod of m, and multiply them and take whole mod of m, right? So this way you can actually avoid the internal overflow conditions, right? Now, in any of this case, there will be situations where you will be trying to calculate multiple different factorials all the time, a factorial, b factorial, c factorial, and so on, in the range of 2 to 80 factorial, or maybe from 0 to 80 factorial, because 80 is the maximum length. So for that reason, I will be pre-computing the entire factorial array in such a way that 0 and 1 is the base case, where I write 0 factorial, 1 factorial is 1, and I can always iterate from 2 till the end, let's say 80, and I will be simply writing factorial at I equals I times of factorial at I minus 1, and I will be keeping it pre-computed so that whenever I want to calculate a factorial, I don't have to calculate it, but I can just return it from the given array. So that will be simple, right? So I hope you have understood this. Let's now look at the equal sum permutation. Now before doing this, I assume that you already know the 0-1 knapsack, and if you are weak in that, then I will suggest you these two problems, the 416 partition equal subset sum and the target sum problem 494, because these two concepts will be helping you to solve this problem. It is the exact same concept, by the way. So this problem is about taking the equal subset sum and applying Fermat's little theorem on top of it. It's nothing else. Fine. Now if I take an example here, the number 1122, the goal here is to count the arrangements or permutations where the odd index sum is equals to the even index sum. Okay, and since the permutation have flexibility of placing any digit at any index, because I can move this one at any place, okay, I can just swap it at any place, and the odd index sum plus the even index sum is equals to the sum of all the digits. That should be true all the time. So if odd index sum is equals to the even index sum, then you can take it as x and you can take it as x, and x plus x is equals to sum of all the digits, which is s, let's say. Then you can calculate this x by saying odd index sum equals even index sum. That will be s by 2, the sum of all digits by 2, right? Therefore the new goal will be to find a unique subset of digits with sum equals to s by 2, instead of converting them into two subsets, okay, where I will say that I will have 1 comma 2 on one side and 1 comma 2 on the other side, 1 2 on one side and this 1 2 on the other side. Instead of saying that, what we can do is we can just form a single subset where I will be pushing half of the digits in such a way that the sum is equals to the total sum of the digits by 2. This is the same concept we have used in the partition equal subset sum, and this is exactly the same logic. Now in example number 1, if you see, we have 1 1 2 2. So at odd locations we can have 1 comma 2. What is odd location? So we will have position 0 1 2 3. So these are the odd locations, and there we can have 1 comma 2 or we can have 2 comma 1. So there are two such arrangements, right? Two arrangements. So we have two ways to arrange 1 comma 2. Again, at even locations, even index, we can place 1 comma 2 or 2 comma 1, right? So for every odd position, if I place odd positions with 1 2, then the even positions can be either 1 2 or 2 1, and still this can remain as 1 2, right? So these are two ways when you take odd positions as 1 2. And if you take odd positions as 2 1, because you can just rearrange it, right? So if you take odd positions as 2 1, then the even positions can again be 1 2 or 2 1, right? So how many arrangements do you get? You get 4 arrangements. So for every arrangement in one subset, all the arrangements in the other subset will be counted. So if there are m such arrangements in the first subset and n arrangements in the second subset, you know that for every one arrangement in the odd set, there will be n number of arrangements in the even set. So for m number of arrangements in the odd set, there will be m times n number of total arrangements, mn. And that is how we wrote that the total ways to arrange in this case will be 2 times 2, which is 4, which is 2 factorial times 2 factorial, because the arrangements in the first set is 2 factorial, second set is 2 factorial, right? I think it is clear. Okay. Now just extending our logic. According to our problem, there are two important factors to consider. The first one is the number of digits is fixed to n by 2. When I create two subsets, each of them should have the size of n by 2. So n is the total number of digits, and we will have n by 2 division in both even and odd subsets, right? So this is possible if the n value given is even. But if n value is odd, like if n value was 5, number of digits are 5, then you cannot split it in 3 by 3 or 2 by 2. You have to split it in 3 by 2 or 2 by 3. So you can take any one of them and it is fine. So you can take floor of n by 2 on one side and ceil of n by 2 on the other side. So that if you have even size of n, then equal distribution will happen. Otherwise, one extra will go on the right hand side simply, right? So that is one logic that we should always maintain while calculating the sum, that the number of digits that you cover should be exactly n by 2 for one of the subset. Okay, we cannot just blindly try the knapsack type solution and try to take any number of digits that I want and try to reach the target sum. That will be wrong. We should also track the number of digits that you have included and make sure that you don't include more or less. It should be exactly n by 2. The second point is the sum of the odd index digits must be equals to the sum of the even index digits. So if that is the case, then you can say that it will be sum of the digits, that means sum of all the digits in the number divided by 2, which I will take as s by 2. If you take the first example, in this case I have 4 ones and 2 twos. So how many digits I have? 6 digits. So if I create two subsets, it will be of size 3 3. So if I take the odd location, because when you have 6 as the size, then you will have 0 1 2 3 4 5 6. These are the indices. Okay, so when I say odd, then that means 1 3 and 5. So at these positions we can place 1 1 and 2. And in how many arrangements I can place them? 3 factorial by 2 factorial. That means 3 ways, because 1 is repeating 2 times, so you have to divide by 2 factorial, right? And at the even locations like 0 2 and 4, I can place 1 1 and 2 in again 3 ways. It is the same thing, right? 3 factorial by 2 factorial. So how many unique representations will happen? 9 unique representations. So the total ways contribution by this split is 9. But this is not the only split. We can have more splits than one, and we have to continuously keep on adding all the ways for different type of split that we get. Another type of split that we see here is 4 ones and 2 twos. But this split is invalid, because according to the first condition we should have half digits on the even side and half digits on the odd side. So on one side you have more digits, on one side you have less digits. So that is why this split is invalid. But there can be valid splits as well. Let's look at another example. Second example. In this case I have 1 1 2 3 3 4. So if I split it into two parts, because how do I decide how to split? You know the sum of the digits. The sum of the digits is going to be 14, I guess. So 4 3 7 plus 3 10 12 and 14. Yes. So the target sum is going to be sum by 2, which is going to be 7. So first thing is your split should have n by 2 items, and also the sum value should be 7. So I can split it as 1 2 4 on one side on the odd positions, and at the even positions I can have 1 3 3. So this rearrangement will give you 3 factorial, and this will give you 3 factorial by 2 factorial, because 3 is repeating 2 times. So total arrangements by this split is 18 ways. Now we can also arrange it in another way, where the odd positions will not have 1 2 4, because what I did is 0 1 2 3 4 5. So at odd locations at 1 3 and 5 I had 1 2 4, and I was rearranging them in any possible order. But another way could have been that I would have placed here 1 3 3 instead of placing 1 2 4, and 1 2 4 were placed on the even positions. So that will give me a completely different set of numbers, right? And so that is also giving me 18 ways. So the total ways in these two possible split is 36, and that is why the answer is 36. I think the idea is clear. Now if the sum of the digit happens to be odd number, then definitely you cannot find s by 2, because s by 2 is not a valid integer in such case. And therefore if you just find sum of the digits to be odd, you can say that the permutations are going to be 0. Like for this given example, the third example, 2 3 2 2. So in this case the sum is 9. Therefore you cannot create two valid partitions of equal sum, and that is why I will answer 0 for this. Okay, so I hope the idea is clear, right? Now let's see the building of valid permutation. So on the next slide I will be showing you the actual building process. Let me just recap the process entirely. So we will be using a 0-1 knapsack logic to build a subset of digits with sum equals to s by 2, which is 6 by 2 if for this particular example equals to 3. And once you have built a valid subset, because we know that the number of items in the subset are going to be n by 2, where n is the number of digits here, which is 4 in this case, so n by 2 is going to be 2. So I will form a subset which having just 2 elements in such a way that if you add up these 2 digits, it will be equals to the sum of all the digits by 2, which is going to be 3. Okay, that is my goal. The target sum must be 3 and the number of digits must be equals to 2 for this particular example. Once you have done, let's say I have created 1 comma 2, then the next step is to count the number of ways to arrange the subset. In how many ways can I arrange? 2 factorial ways, right? In 2 factorial ways, which is 2. And we need to add this to the total number of ways to arrange. So I can arrange it in 2 factorial ways. What about another subset? Because there will be another subset which is also 1 comma 2, and I can also arrange it in 2 factorial ways. So the total ways when you create 1 comma 2 on one side will be equals to 2 factorial multiplied by 2 factorial, which is 4 ways. 4 ways. But there could be other valid split too. In this example, there is no another valid split, because if you say on the even set you have 1 comma 2 and on the odd set you have 1 comma 2, and you argue that I will swap these numbers, then still nothing is going to change. It is the same number which is getting generated. You should generate a unique number in the permutation, and that is how the ways will increment. You cannot just say that 1 comma 2 from here moves to the even side and I will be counting it. It will be a duplicate counting. Okay, so please avoid that. Fine. So we need to count the number of ways per split. I had already shown you in the previous example that you can have more than one split. So this is the first split and this is the second valid split, right? While the previous example only had one valid split and this was invalid split. In this case, there is only one valid split. Fine. Now I will be defining some variables here. Like, you know that the slots to be filled will always be half and the target sum will always be s by 2, as I have explained. So there are 3 variables that you should consider. One variable is digit. That means which digit are we currently assigning. We will be trying all the digits from 0 to 9 because the problem statements already mentioned that we can have the digits from 0 to 9. Okay, so we can try all those digits from 0 to 9. We will be considering a variable called leftover, which will show how many more digits do we need to pick in the first half, because we know that we have to pick n by 2 number of digits, right? So let's say in this example we had to pick 2 digits. So the leftover value will be equals to 2. And if I happen to choose a digit, because I will be trying all combinations, right? Something like 2 to the power n. So if I happen to choose, let's say I will take 1 in my even subset, then the leftover digits that needs to be included will be decreasing by 1 and it will become only 1. This is to make sure that when the leftover reaches to 0, then I should return back in my recursion rather than trying to include anything more, because you cannot include anything more than n by 2. So this is a check on that. This will maintain that we always include n by 2 items. Okay. Now the target is about how much sum is left to reach, because we have 2 conditions. As you remember, I mentioned it previously that we should take care of the number of digits being exactly equals to n by 2, and this is taken care by the leftover, and the sum of the odd index should be equals to sum of even index, which is equals to the total sum of all the digits by 2, and this is taken care by the target value. So if the target value here in this case was equals to 3, which is true, right? Then if I had included a 1, then the target value will decrease by 1 and it will say that, okay, you know, now your target has changed from 3 to 2, and the leftover value, which was 2 initially, because I had to include 2 digits out of 4, if you include this one, it will change to 1, which will say that I have to only include 1 more digit, and the target is saying that I have to have 2 more sum. So can I include a 1? Immediately looking at the target and leftover, you will know that I cannot include 1, because yes, I can include it based on the count of digit, but I cannot include it based on the sum. Okay, because the target sum is 2. And if I ask you, can I include 3? Yes, according to the leftover, you can include one digit, so you can include 3, but according to the target sum, if you include 3, then you will exceed this value 2, and so you will not be exactly stopping at a s by 2. Okay, so I hope you have understood these 3. The digit will take care of what digit we are currently trying. The leftover will tell us how many digits I have to include more, and the target will tell us what is the leftover sum to be reached. Okay, how much sum should I add more? So having understood all these points, let's see that the digits that we can try at any position will be, let's say, I, and so I will start from 0 and it cannot exceed the minimum of leftover, the frequency of digit, comma, target by a digit. You have already understood that the number of digits that you can include cannot be more than the leftover, because the leftover will show how many more digits do you want to include, isn't it? But if I'm trying, let's say, digit 1 and the leftover value is 3, then can I include 1 3 times, or can I include it 2 times or 1 time? How many times can I include? Even if the leftover is 3, I may not be able to include 1 3 times, because it will also depend on the frequency of 1 in the actual number. Okay, so sometimes it will happen that the leftover value is more, but the frequency of the digit is less in the actual number. So you cannot include it as many times as you like. Okay, so it has to be minimum of leftover comma frequency digit. Now let me ask you one more thing. Let's say that the target value was 2. Okay, target value was 2, the leftover was 3, and let's say you are trying to include digit 1. Okay, the leftover was 3, the frequency of 1 was equals to 4, and the digit was equals to 1. So if the target was equals to 2, then how many times can you include 1? You cannot say that I will include it leftover times, or I will include it minimum of frequency of 1 comma leftover times. No, because if you do that, then you will be including 1 3 times, and so you will be over including and not exactly including target sum 2, because if you exceed, you will go beyond s by 2. If you remain at a lower place, then you will be not able to form s by 2, right? So exactly you have to form this target 2. So that is why this target will also come into picture. Okay, so the target by whatever digit you are including, that means 2 by 1 has to be included 2 by 1 times. Why 2 by 1 times? If this digit value was, let's say, 2, and the frequency was 2 was 4, okay, and the leftover value was 3, then how many times this 2 can be included? This 2 can be included minimum of 3 comma 4 comma 2 by 2. That means one time only. Okay, because if you include it more than one time, then you will exceed the target sum, and so you are not able to reach to the target value, right? Because we know that all the digits are positive. It is starting from 0 to 9, right? 0 is not a positive number, but still there is no negative number, right? So it cannot decrease back after you have included something, and that is why this condition also holds true. So all these 3 conditions have to be taken care separately, which will be telling you starting from 0 what all digits you should try at a particular position in a set. Okay, and that variable is the digit which will be telling you what you are trying. I hope all these variables are clear, and once it is clear, let's understand the recursion. Okay, so in this case I will be taking a simple example. The big example will be very difficult to visualize and also draw. So in this case I have 1 1 2 2, and I will be starting at position number 0 and moving from left to right. So the node values here are actually digits, and if you look at T is the target sum that I need to achieve, and L is the remaining digits, or you can say the leftover remaining digits to be included, whatever we saw previously. So initially I know that the sum of all these digits, sum of all the digits is 6. So what is s by 2? It is equals to 3, and that is why the target value is 3 and the leftover value is 2, because the number of digits here is equals to 4. So that means half of the number of digits is 2, so leftover value will be 2. Now if you start trying the values for the first position, like what will be the subset size? The subset size will be 2, and if you start with the first position, then what all numbers will you try? It will be 0 to minimum of leftover comma frequency of digit comma target by digit. So minimum of, what is the leftover? The leftover value is 2 comma leftover value is 2. What is the frequency of the digit? So first of all, you have to parse and find the frequency of the digit. The frequency of 0 is 0, right? So it does not matter what is the other value, this minimum is going to be 0. That means 0 will be included 0 times, and we will be moving to the next digit to try. Now we will be trying with 1. Okay, so how many times can 1 be included? Well, you take the minimum of leftover, which is 2, because I did not include 0. 0 has been included 0 times, and that is why the target and leftover will not change. Now 1, how many times can it be included? So leftover is 2. What is the frequency of 1? If you look at the map, then I have not built the map here, but you can build the map and you will see that 1 has occurred 2 times. And what is the target sum? So the target sum is 3. Okay, so target by what is the value? 1. So this will be equals to 3, right? So 2 comma 2 comma 3 is going to be 2, and that is why you can include 1 maximum 2 times. So even if you include it maximum 2 times, I will be trying from 0 to 2. Okay, we will be trying all the possibilities. So let's try to include 1 0 number of times, and if you do that, then you will be reaching to digit 2. The target and leftover is not going to change because you haven't included 1, and at 2 you find the frequency of 2, again it is 2, right? So I'll be taking minimum of leftover comma, the leftover value is 2 here, right? Leftover comma frequency of 2, which is 2, comma the target sum by 2, which will be equals to 1. So you can include 2 maximum 1 number of time. So you can take either 0 time or 1 time. Whatever option you choose, 0 time or 1 time, you will go to actually digit 3, and you know that beyond 2 there is no other digit available in your actual number. So you will never be able to include any digit from 3 to 9, and so your target and leftover is never going to change. And when should you stop? When your leftover is equals to 0 and the target is also equals to 0, then only at that time you know that I have included n minus 2 digits and I have made the target sum s by 2. So this is the stopping condition which will increment your count of number of ways. If you stop at any other condition, then that will not increment, that is not valid. So in this case, this will be returning a 0 count. This will be returning a 0 count. Okay, 0 count. This will be returning 0 count. Okay, and this will also be returning a 0 count. Now you are at 1. At 1, you have tried to include 1 0 times, and you can include 1 maximum 2 times. Now you will try to include 1 time, and if you do that, the leftover value, that means the number of digits to include, will decrease by 1 and it becomes 1. The sum value, target sum to be formed, will decrease by 1 and it becomes 2. Okay, at this 2, how many times can this 2 be included? So this will be equals to minimum of whatever is the leftover, that is 1 comma frequency of 2, that is 2 comma the target sum 2 by the digit, which is 2. So this will be equals to 1. So you can include 2 maximum 1 times. So you can also include 0 times. So I will try all possibilities by including 2 0 times to 1 times. So if I include 2 0 number of times, then my target and leftover value is not going to change. And once I reach to digit 3, beyond that nothing is possible to be included because it is not even present in our number. So this will be returning value 0. This will be returning value 0. Okay, now if I include 2 1 time, then you see that the leftover will become 0 and the target is also becoming 0. Okay, so since they both become 0, so at this point of time, at this node, you know that you have hit a valid point. You have hit a valid arrangement. Okay, so if you have hit a valid arrangement, what you will do is you will count the number of arrangements there are. So if you have 1 1 2 2, and if you formed 1 comma 2 as one set and 1 comma 2 as the other set, then what you can do is the number of ways you can arrange is 2 factorial into 2 factorial, and that will be 4. So from here you will be returning a value 4. Okay, you will be returning a value 4, and this will be returning a value 4. Fine. Now on the other side, this 1 could be included two times, right? So if I include it 2 times, then the L value, leftover value, will become 0 and the target will become 1. So after this, no further call will be possible. This branch will not run because If the leftover becomes 0, then at that point you will stop and say that if the target is 0, then you will return the number of ways to arrange. Otherwise, you will simply return a value 0 in this case. So what will this 1 return? 0 plus 4 plus 0, it will return 4, and this will return 4. So the total number of ways to arrange 1, 1, 2, 2 is 4 ways. And this is the recursion method to do that. Now if you closely monitor this, then there are 3 variables which will affect your result. And those 3 variables are target, leftover, and the digit that you are trying. Okay, there are 3 such parameters. In this case, the example is small. I could not show you the repeating subproblem, but if you take more digits, then the recursion tree diagram would be larger and you will be able to see repeating subproblems. Okay, so these are the 3 variables on which your result actually depends, and therefore we can store the answers for all these subproblems. And I will say that I will create a memoization table, a 3-dimensional table, with the first dimension being the digits, which will be ranging from 0 to 9, the second dimension being leftover, which will be ranging from 0 to 40, and the third dimension being the target. The target can be maximum 40 times of 9, because all the digits could be 9, isn't it? And there can be no more than 40 digits. Why I am writing all these numbers? Because if you look at the constraint, the num's length is maximum 80. So if your n value is 80, and if you know that I want to form a subset of n by 2 size, then the maximum size of this subset is going to be 40, right? And that is how I'm writing it. And all the digits can be maximum 9. So the maximum target sum that you can have is 40 times 9, simply. And that is why I have written here 40 times 9. So I will be taking a memoization table of size 10, 40 plus 2. This plus 2 is for my own safety, okay? And this target also has 42 times 9. And assign all these values. This is a 3-dimensional table, right? So I'm not drawing it. It will be difficult for me to draw. So all these will be filled with the value -1. Why with -1? Because the count value cannot go below 0. It is impossible. So I'm just filling the table with impossible value, so that if I look at a value and if it is not -1, that means the answer has been calculated, and just simply return that. Otherwise, if I see a -1, then I will try to follow the recursion. Okay. Now the total number of subproblems in this case is going to be 10 times 40 times 40, which is in terms of n, you can say 10 times n by 2 times of n by 2. And therefore, you can say that the space complexity is n square. It is not n cube. Okay. Even though we are taking 3 dimension, the digit is from 0 to 9 always, all the time. So this is order of n square. And in each state, we try the maximum leftover number of digits. Okay, that means n by 2 digits. So this is saying about the branching here. The branching can go to maximum of n by 2. Okay, to maximum of n by 2. And that is the reason that since the branching can go to maximum of n by 2, we have to run a for loop here. Okay, the depth of this entire tree cannot be more than 10. It will be always less than equals to 10, because there are only 10 digits. But the branching of it will be of size n by 2 in the worst case scenario. And we have to run a for loop. So if you have to run n by 2 size for loop for all the subproblems, where the total number of subproblems are n square, then don't you think the time complexity is going to be n cube? It will always be true, right? So this is the entire approach by using recursion, Fermat's little theorem, modulo multiplicative inverse, and some basic modulo arithmetic. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, if you look, the main function is the count balanced permutation. Now let me define all the global variables here. So I am using LL for long alias, and the mod is 10 to the power 9 plus 7. And I have defined total ways to permute, which will be pre-computing the number of ways to arrange one side with the other side. Okay, it will just be multiplying. I will be pre-computing factorial, inverse factorial, and I will be pre-computing the frequency, which is our frequency map. And this is the memoization table. I have already explained you all these values. the length is maximum to 280, and since I am just considering n by 2 length, and that is why it is 40 plus 2. The maximum digits are also n by 2, and that is why it is 42 times 9. You can also write 40 times 9 as well. I have just taken 2 for safety. So these are all my global variables. If you look at the important functions, this is the modulo multiplication function, where I have just converted it according to my modulo arithmetics, right? That I had already explained you. You see this? According to this formulation, I am trying to multiply. Okay, that is my modulo multiplicative function. Now if you look at the compute factorial, then this is just pre-computing the factorial using the modulo multiplier. Okay, now if you look at the binary exponentiation, you already know how it works, right? So you can just revisit my video if you don't know this. If you look at the compute inverse factorial, this is the same, right? What it is trying to do is, it is trying to calculate a to the power of m minus 2 simply, right? So that is how you can calculate the inverse factorial under modulo m. Okay, so I hope you have understood this, computing the inverse factorial as well. These are all the pre-computations, and binary exponentiation is used on the go whenever you require to compute the inverse factorial. Once that is done, let's look at the main functions here. So there are two main functions. The one is the count balanced permutation, where you are given the nums value, find the number of digits in nums, the sum, and the frequency of each of the digits. So iterate through all the digits and find the sum and the frequency of all the digits. After that, if the sum is an odd number, then you simply return 0 permutations. It will not be possible to get sum by 2. Otherwise, you take the target as sum by 2 and you pre-compute the factorial. You pre-compute the inverse factorial. Once everything is done, we will be also pre-computing the total ways to permute. So if you have 1 comma 2 on one side and 2 comma 1 on the other side, it will be 2 factorial by 2 factorial, that I will be pre-computing and saving it in total ways to permute, so that if I find a valid permutation, then I will just add this whatever is the pre-computed result, which is 4 in this case, right? 4 will be saved. I will be showing you above, and then I will be taking the DP table and assigning -1 value to all the cells, and after that I will be calling the count permutations. Okay, so if you look at it, then I am trying with the digit equals to 0. I will be starting to try from 0. The number of digits, that means the leftover value will be n by 2. That means half of the digits must be filled in the set, and the target, which is the target sum, target has to be reached. Okay, let me now show you the function here, which is the count permutation. So in this case, we get the digit leftover and target. If the digit reaches to 10, that means I have tried everything from 0 to 9. Okay, and if everything has been tried, then I will be checking with the leftover value of, if it is 0, then simply check if the target is also 0, then we have found a valid subset, and then return the total ways to permute. Otherwise you return 0. That means it is invalid. And if leftover is not 0 and you have reached to digit number 10, then you have tried all the branching and this is invalid branch because 10 is not a digit, and you return 0. If the sub problem is already calculated, it is not -1, then you just return the value. Otherwise, for any particular digit, let's say it is 2, you need to see how many times you can try. So that will be minimum of leftover, comma, frequency of the digit, comma, the target by digit, if the digit is greater than 0, right? Because otherwise division of 0 problem will come. So I think this I have already explained you and you have understood. Based on the include count, we can iterate by trying from 0 to include count number of times. Okay, we can try all these numbers, and I will be taking an answer which is storing the number of ways. So the ways for the current digit will be actually equals to multiplying the inverse factorial, because what this inverse factorial is doing is, if your set was 1 1 2, on the other side, let's say you have 2 1 1, okay, then in the previous case I said that, let me show you. In the previous case here, what we were trying to do is just take the factorial of floor of n by 2 and multiply it by the factorial of ceil of n by 2. So what this is giving, according to these sets, it is trying to give you 3 factorial into 3 factorial, right? But is this correct? 6 into 6, which is 36. is this correct directly? I mean, it will not be correct, isn't it? Because you cannot just say that 112 is a valid set means there are 36 ways. No. Here there are 3 factorial by 2 factorial ways. And here there are 3 factorial by 2 factorial ways. So if you multiply them together, this is 3 ways only. And this is only 3 ways. So there will be 9 ways. So in order to compensate for these repetitions, we have to multiply by the inverse factorial. Okay. So if you do dry run with your pen and paper, I think you will be able to understand why we are doing this inverse factorial multiplication. And then we need to just do the recursion. If we have tried the digit, then we go to the next digit to try, and the leftover will be decreasing by the number of digits that you have included, and the target will be reduced by, if the digit was 2 and if you have included it 3 times, then the target will be reduced by t minus 2 times 3. That is what it is doing. And simply once you have calculated the number of ways, then you just save it into your memoization table and return back. So I hope this entire approach is clear, and if you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.